Hello, my name is Moses Ajay. I'll be presenting another solution for the exam practice question for food process technology. The second question is on a plate heat exchanger. Now, milk is to be pasteurized at 72 degrees Celsius for 15 seconds using a plate heat exchanger. Now, the heat exchanger has cooling, regeneration, and heating section. The inlet temperature of the milk is 5 degrees Celsius and it leaves the regeneration section at 48 degrees Celsius. The flow rate of milk is 1.5 kilogram per second and the inlet temperature of the water is 90 degrees Celsius and the mass flow rate is 1.0 kilogram per second, assuming that heat losses are negligible. Now, this is very important. Heat losses are negligible. Determine the heat supply in the regeneration section and also in the heating sections. Determine the numbers of plates in the regeneration section and the numbers of plates in the heating section. Now, we're also given the area of each plate, which is 0.5 meters square. Now, we're also given the mean heat capacity of milk, which is 4.0 kilojoule per kilogram per Kelvin. Now, this is the same thing as 4,000 joule per kilogram per Kelvin. Now, the mean heat capacity of water, 4.2 kilojoule per kilogram per Kelvin. And the overall heat transfer coefficient in this section, that is to say, in the cooling section, regeneration section, and heating section, the overall heat transfer coefficient is given to us as 2.1 kilowatt per meter square per Kelvin. Now, in order to understand this problem, like I said earlier, you need to understand what is given to you. Then, and in order to illustrate that, so this is what is given to us. We are given the plate heat exchanger. It has 3 different sections: cooling, regeneration section, and heating section. Now, for us to understand the problem, you need to understand the working principle of a plate heat exchanger. Now, the whole essence of regeneration section is to bring about saving energy. Now, you've heated your product here. Rather than sending it to the cooling section, you send it via the regeneration section in order for the raw product to extract part of the heat in the processed milk. Now, there's going to be a form of heat exchange in this section. Heat is going to be transferred from the hot milk to the cold milk so as to preheat the cold milk. Now, the only sense of that is to reduce the energy requirement at this section. So the operating cost of the machine goes down and so on and so forth, which is very good for the environment. Now, we know that our T1 is the inlet temperature for milk, and then M1 is the mass flow rate. You can call this anything you want to call it, but I prefer to call it M1 for mass flow rate of milk, and then I have M2 for mass flow rate of the for hot water, and then T6 for the inlet temperature for hot water. So this is what, and again, you remember we are given the table, so to take note of that. Then, now the very first thing we have to do is to determine the heat supply in the regeneration and the heating section. That's the first thing that we need to calculate. Now, in order to do that, you need to understand 2 things. Now, the very first thing you need to know is heat transfer into or out of a moving fluid. Now, there's a different formula for heat transfer into or out of a moving fluid, and also for heat transfer through a medium. That is an heat exchanger. That's I'm referring to heat exchanger. Now, heat transfer into or out of a moving fluid is going to be determined by Q equals MC dt. Now, M is the mass transfer rate. Mass flow rate, sorry, where M is mass flow rate of the product or of the fluid. C is the heat capacity of the fluid, where the T is the change in temperature of the fluid. Now, for the second one, if you want to calculate the heat transfer through a medium, you will need to use this formula, the formula we used earlier in question 1, which is Q equals area, the cross-sectional area of the medium, the change in temperature, and then the summation divided by summation of the thermal resistance. Now, here we are not giving the thickness or the thermal conductivity. All we are giving is the overall heat transfer coefficient. Don't forget that our our Q can be expressed as UA delta T, where our U equals 1 over RT, or where our summation RT equals 1 over U. So if you remember this, you know that these two formula are the same. This formula and this formula are the same. Now you remember, this is the one of the reasons why I do not include my A in the computation of thermal resistance, so that I can conveniently express my U in terms of RT. Now you can see it's possible to express our U in terms of RT just because in the computation of our thermal resistance, area is not included. So you know, if you just take note of these two formula, we're going to be using the two of them. Now one, if you are calculating the heat into the heat you transfer into or out of a moving fluid, you need this. So this is the regeneration section. Now we want to find out the heat supply in the regeneration section. Now you know that the milk is going to be entering here at 5 degrees Celsius and is leaving at 48 degrees Celsius to preheat for preheating. Then before it goes into the heating section, we don't want to include the heating section so as to make the to simplify the scenario. Then the milk is flowing at the rate of 1.5 kilogram per second. Now we can see that at this end, at the coast side of the regeneration section, we know the inlet temperature, we know the outlet temperature, and we know the flow rate. That shows we can calculate the heat supply at the regeneration section. Now, because the heat supply in the regeneration section, let's call that one QR, is going to be heat supply from the hot milk side. It's going to be the heat being supplied from this side. Because don't forget the initial assumption: no heat loss, no heat loss, or let's say it is negligible. Now let's say it is negligible. Don't forget that. Before we can, if this formula is valid, because the assumption is there's no heat loss. Now the heat supply at the regeneration center, section, is going to be the heat supply from the outside of this section, and that same will be equal to the heat absorbed by the milk in the cold side, because heat that is supplied here is going to be transferred through the medium, through the exchanger, through the plate exchanger air, and it's going to be absorbed by the cold side, by the milk in the cold side, because the assumption is no heat loss. Now, so, and again, like I said, it's going to be the heat transfer through the heat exchange plate in the regeneration section, and because we are talking about through the medium exchange plate, so you're going to be using this formula: Q equals UA delta T. That's the formula through the heat exchange in a plate. But now we want to find out, because now we know the mass flow rate of the milk, we know the temperature difference, we know the specific capacity of the milk. So this formula, we can't use this formula at the moment. We can use the heat supply to the heat. Sorry, we can use the heat absorbed by the milk. So we can say our QR equals heat absorbed by the milk. All you need to do in order to solve a problem is just to take one, and just to take two of them. I need this, and I'm picking this because I know the parameter to determine the heat absorbed by the milk in the cold side. I know the parameter, because the parameter I will need to determine that will include my M, the mass flow rate of the milk, the heat capacity of the milk, and the change in temperature in the cold side. And by the time you put in the value, because I know the temperature difference to be 48 minus 5, put in all those values, and you will discover that our QR equals our 1.5 kilogram per seconds multiplied by 4,000 joule. Now here I'm using 4,000 joule per kilogram per Kelvin, because I want to have my answer, my final solution, in SI unit. I do not want to disturb myself. I want to have my final solution in SI unit. So the change in temperature is 48 minus 5. Now this is the heat absorbed by the milk in the cold side. Now we are going to have this, and I'm having my final answer to be joule per seconds. Now don't forget, your joule per seconds is the same thing as watt. Just for example, somebody is bearing rope. It can be it can be Kelvin. One person can bear two names. Now the unit of heat is joule per seconds. It can also be watts. It can also be kilowatts. So we can have one person bearing different names. It's just the same thing for our variables in mathematics. So we have 258,000 joule per second, or 258,000 watts, or 258 kilowatts. Now because kilo is 1,000, so it's the same thing. So we have the heat supply in the generation section to be 258 kilowatts. Now that's question number 1 solved. Now the heat supply in the heating section. Now we know that in the heating section the milk is leaving the regeneration section at 48 degrees Celsius. It's going in there and it's coming out. You know it's coming out because we are told that it's going to be pasteurized at 72 degrees Celsius. It's coming out at 72 degrees Celsius. So we know the inlet temperature for the milk and the outlet temperature for the milk. Now it's supplying the heating section. Now what is supplying the heat is the water. The hot water here is supplying the milk. Is supplying the heat. It's supplying the heat. The hot water that is coming here is supplying the heat. The hot water is coming in at 90 degrees Celsius. T6 is 90 degrees Celsius. It's supplying the heat. But unfortunately, we do not know our T7. We do not know our T7. So we can't use the parameter for that to calculate the heat supply at the heating section. But we know the recipient. We know the data. We know the information about the recipient of the heat, which is the milk. Now we know the milk is going in at 48 and is leaving at 72 degrees Celsius, and we know the mass flow rate of the milk, and we also know the mean heat capacity of the milk. So we can actually use that to calculate the heat to calculate the heat supply in the heating section. We can use that to calculate the heat supply in the heating section. Now the heat supply in the heating section will be equals to heat absorbed by the milk in the heating section. Now, and that will be QH. I call that QH will be mass flow rate of the milk, specific capacity of the milk, times temperature difference in that section. And the mass flow rate is the same thing as 1.5. Then the milk capacity of the milk is 4,000. Then the change in temperature is 72 minus 48. So from there you will have the heat supply in the heating section, which is 144 kilowatts. Now we've been able to find the heat for question A. Now we want to find the numbers of plates in the regeneration section. Now before you can calculate the numbers of plates in the regeneration section, you will definitely need to know your temperature difference, the logarithm mean of your separation difference. Don't forget that the heat supply in the regeneration section is the same thing as heat supply by the hot milk. That's the heat supply by the hot milk, and that must be equals to the heat absorbed by the cold milk, like I said earlier, and that will be equals to the heat transfer through the exchange plate in the regeneration section, and it is given to us as this. Now don't forget that our Q will be expressed as U multiplied by the area, the total area in the regeneration section, the area the area through which it is transferred in this section. That's the AR, and our DT is the logarithm mean temperature difference in the regeneration section. Now AR is overall heat transfer area in the regeneration section. Now if you know the overall heat transfer area and you know the area of each plate, you can actually calculate the total numbers of plates. Now but for us to determine delta TL, we need T4. We do not know T4. We need to find the T4, because if you know T4, then we'll be able to say, okay, for example, we can't say this is the temperature difference. We can't say this is the temperature difference. We need to use the logarithm mean temperature difference in the regeneration section. And how do we do that? Now you know that our Q equals heat supplied by the hot milk in the hot side. Now the heat supply, the heat, you know, we've been able to calculate that the heat absorbed here in the cold side is 258. This same heat must be the same heat supply by the hot side, because we said that the heat loss is negligible. So if the heat loss is negligible, the heat you absorb from here will be the heat that is, the heat absorbed in the cold side will be the heat supply by the hot side. So which implies that QR is equal to 258, and that will equals to MC theta. Now I'm dealing with hot side now, so we're gonna have 258, which is the heat supply. I've converted it back to the SI unit. This is the mass flow rate of milk. This is the heat capacity of milk. Then 72, which is the inlet temperature minus outlet temperature T, which is T4. So we need to find our T4. Our T4, if you solve this, you will discover that this is going to be this. I've tried to cancel out kilogram is cancel kilogram, minus seconds here, seconds raised to minus 1, seconds raised to minus 1. They can cross out each other because they are on the other side of opposite side of the equation of the equality side. Then kilogram here is raised to minus 1. This kilogram is not raised to minus 1, so they can cross out each other because they are on the same side. Now this kilogram raised to minus 1 is like saying joule divided by kilogram. So kilogram is denominator here, is numerator here. They can cancel out each other. Now, so you have this. Your Kelvin is down. Your Kelvin is down, so it's going to go to the other side, which is why I have it here. So by the time you solve the problem, you divide through by 1.4, 1.5, and 4,000. You will finally have your 72 minus T4 equals 43. Then minus T4 will be 43. Will be 43. Now this is positive. By the time it goes to the other side of the equation, it turns to negative. Now that shows that minus T4 is equal to minus 29. Then minus, we cancel out minus, you have T4 to be 29 degrees Celsius. So we've been able to find out our T4 now. Our T4 is 29 degrees Celsius. So we find out our T4. So we need to find out our logarithm mean temperature difference in the regeneration section. Now to do that, we know that we need to draw something to show that you need to draw something here so that you can understand how to do that. Now, you know, let's say this is our cold milk moving from here to here. Then our hot water is moving from here to here. So that shows that our cold milk is coming in at 5 degrees Celsius and is leaving at 48 degrees Celsius. Now our hot water is going at 90 degrees Celsius. Sorry, our hot milk, because this is regeneration session. Our hot milk is going in at 72 degrees Celsius and is leaving at 29 degrees Celsius, which is just what we have calculated. So we can find out our DT. Our DT1, our change in temperature at this point, and we can also find out our change in temperature at this point. Our change in temperature at this point, DT1 will be 29 minus 5, which is 24, and DT2 will be 72 minus 48, which is also 24. Now, interesting. Now, since our change in temperature equals DT2 equals 24, sorry, DT1 equals DT2, and they are equals to 24. The implication of that is that this formula is not going to be needed because it's uniform all through. Our change in temperature is uniform all through, so we do not need logarithm mean temperature difference because our temperature difference is uniform all through. So this formula is no longer needed. So our DT, but in some situation you would definitely need this formula, but now we do not need the formula, but I'm sure we will definitely need the formula in the heating session. So our DT logarithm mean equals 24 degrees Celsius, so, or 24 K, so just can put 24K there. So we have that as our final answer. So by the time we put 1258,000 for QR, the overall transfer coefficient in the session is 2.1. But we know I want to convert that to watts per meter square per Kelvin, so I multiply it by 1,000. So this now turns to watts rather than kilowatts. Now multiply by AR, multiply by 24, which is the temperature difference. So you have this. I try to rearrange. I try to cancel out all those things, all the units that I do not need. Then divide through by this is what we have. We want to find out our AR, so we need to divide through by 24 and 1000 and 2.1. So by the time you divide by that, so you have your AR standing alone. Then divide this by the 258,000 divided 258,000 258,000 divided by 2.2 divided by 1000 divided by 24. So you have AR, which is the overall area in the regeneration section, to be, we have that one to be 5.119 meters square. So we have that. So our numbers of plates will be AR divided by area of each plate. Our AR is 5.119 and our area of each plate is 0.1. So our numbers of plates will be 10 plates. Mathematically, theoretically, is 10 plates because it's 10.4 is 10 plates. But in real life situation, I would say this is going to be 11 plates in practice, because you need more than 10, and each is going to be lost. So you definitely need more than 10 plates. Maybe something like 11 plates is fine. 11 plates is fine, but mathematically this 10 is correct, but in practice I would say 11 plates. Any of the two will be marked right. So I think both of them are correct. This is mathematically 10 plates, theoretical in practice 11 plates. Now, to calculate the numbers of plates in the eating session, so this we're going to follow the same principle, but now the heat here is not the heat in the eating session is being supplied by hot water, not by hot milk. So that's the different scenario that we have here. Now we know that the heat supply in the heating session QH, which is what we've obtained that to be 144 kilowatts. Now it's going to be heat supplied by the heating medium. Now and our heating medium here is water. Now, and that same heat supply must be heat absorbed by the milk in the heat session, just because no heat is lost. So, and that will equals to heat transfer through the heat exchange plate in the heating session. So we have our QH to be U multiplied by area multiplied by logarithm mean temperature difference in the heating session. So we have now, because we need to determine delta T LM, but because we do not know T7, we need to find out what's our T7. So we're going to use the same principle. So how do we do that? You know that heat supply by the heating medium is 144. That same heat supply must be equals to mass of the heating medium multiplied by the heat capacity of the heating medium times temperature difference of the heating medium. Now the mass of the heating medium in this scenario, the mass flow rate of the heating medium in this scenario is 1. So the heat supply there is 144,000. The mass flow rate of water is 1. Then the mean heat capacity of water is 4,200 joule, and the temperature difference will be 90, which is the inlet temperature, minus outlet temperature, which is T7. So you have this. By the time you put all those factors in and you find out that our T7 equals 55 degrees Celsius. So we now have our T7 to be 55.7 degrees Celsius. That's our T7. So we know our T7 to be 55.7 degrees Celsius. Now, to calculate our logarithm mean temperature difference in the heating session, we're still going to use the same principle. Now, let's say this is the milk and that's the water. Water is flowing from 90 to 55.7, and the milk is flowing from 48 to 72 degrees Celsius. Water is 90 to 57.7. So we need to find the temperature difference delta T1 and temperature difference delta T2. So delta T1 is 7.7 K and delta T2 is 18. No, delta T1 is 55.7 minus 48. Delta T2 is 90 minus 72. So we discovered that these are not the same. So this formula is very important. So our delta T2 is 7.7 minus 18, which is delta T1 is 7.7 minus delta T2, which is your calculation. In your calculator, in your scientific calculator, you press this first, open the bracket, press 7.7, press this in division 8, close the bracket, press equal to, you will have your answer for the denominator. But this is programmed in a different way. But if I want to do this, I'll just press 7.7 divided by 18 equals this. So the ln of that is what I have in my denominator. So 7.7 minus 18 divided by what you have here will give you your final answer. So that's what we have. Now we have our delta TLM. So we know that therefore our 144,000 will be equals to, we've been told that the overall heat transfer coefficient is 2.1, which is 2.1 times 1000 degrees 1000 watt per meter square per Kelvin. Now our area for the heating session, then times the temperature difference, which is 12.13. So you have this. Then by the time you divide through by this 12.3, 1000 and 2.1, you do it for both sides, your AH will be standing. Then this divided by this will give you your final answer, which is AH equals 5.653 meters square. But you need to find the numbers of plates. The numbers of plates will be AH divided by area of each plate, and that will give you 11.31, which is 11 plates in theory, but in practice it's going to be 12 plates. And I hope you understand this. And if you have any question, please be free to get in touch with us. And for references, you can use this. And if this approach has been of any help, please email us your feedback and your suggestion. Many thanks. Bye.